All right, welcome back to part 2 of 5 realities. This is presentation 2 for CS224. Let's jump right in. So again, we've been discussing 5 realities that are motivating what we're going to be studying in CS224 and some of the things that we're going to want to understand as programmers of systems. We've already discussed the fact that ints are not integers and floats are not reals, and that knowing assembly is for everyone. That anyone who is developing software and working with computing systems in that kind of way should understand the assembly language of the machine that they're working on. And we just gave some kind of high-level overviews. They were specific examples, but they were high-level examples of the kinds of things that you want to do. And we'll dive in more to this, obviously, as the course goes on. Today we're going to talk about, in this presentation, the fact that memory matters. We generally think of memory as this kind of black box, right? This abstraction in the background. And we want you to understand and realize that that's not the reality, okay? And we cannot always think of memory just as this infinite resource in the background. My slide's a little messed up here, I apologize. In a minute, I will talk about the fact that memory performance is not uniform. But first, let's begin by talking about the fact that memory is not unbounded. We have a limited amount of this resource, and so it has to be managed properly. Now, much of the work of managing memory on a system is going to be handled by the operating system. But it's not magical, and we need to know what the operating system is doing because that will affect the way that our programs execute at runtime, okay? Many of the applications we're going to write are going to be memory dominated. In other words, much of the time that they actually spend in execution is spent moving data, moving information around. And so if you're spending most of your time working in memory, you need to understand how memory works. Now, again, the operating system does a lot of the work for managing the memory for us on our systems. However, much of that work is done in response to requests that we make. And so in many of the languages that you will learn, you will have responsibility actually for allocating and deallocating memory. So even though the operating system does the heavy lifting there, you still have to be the one instructing it to give you memory or put it back and so forth. And so you need to understand those mechanisms. You also need to understand the implications of the choices that you make. The OS is going to try to do what you want. And what you want might not be wise. And so the more informed you are, the better a job that the OS can do for you, and the better that your functions, have a hard time, that your programs will perform. Memory referencing bugs, they can be especially nasty, okay, and for a couple of reasons. Ultimately, one of the most troublesome problems with memory errors is that often they don't show up immediately. And what I mean by that is something goes wrong, but it takes some time before you're actually aware of the fact that something went wrong. And that's terrible because you may be in a completely different portion, if you will, of a program's lifespan when the fact that something went wrong becomes apparent. And because of that, you don't know exactly when or where it happened. So it can make it very difficult to find. And then finally, the first thing you saw, but the last thing I'll talk about on this slide, is that memory performance is not uniform. Again, there's this memory system. It's not infinite, and it's not even homogeneous. Some of the memory on our computers is really fast, and some of it is really slow relative to the processor. And obviously we want to use the fast memory as much as possible. And so understanding how a cache works and the virtual memory system in general can really affect how efficient our computer programs are. And so knowing these things, we can adapt our programs to the particular memory system that we're working with and have enormous effects on the speed. So let's talk about one of the first issues I discussed on the previous slide, and that is memory referencing bugs. So here's an example. In this case, we've got a data type up here. It's just a simple struct, and within that struct, we've got, I'm going to change my color here so it's easier to see. Alright, so in this structure, we've got an array of ints, and we see that there are 2 of those, and that will be important. And then a variable identified as D that is of the data type double. Okay. Now, I should point out that's a double precision floating point number. We're going to assume a 32-bit system here. And so each int would take up 32 bits, and our double will most likely then take up two 32-bit words. Now, we've got a simple function here that's going to utilize this data type. So the function is called fun, and it takes one argument, an int, that we will use down here to dereference this array A. We've created, on this line, we've created, I need a better color yet, that doesn't show up real well. Here's a really, yes, that's a very nasty looking yellow, that'll show up. Okay, so we've got this, this variable s of the data type struct t that we defined up above. And you'll notice we're using this keyword volatile. I don't expect you to know a lot about that at this point in time, but just as a brief synapse, what this keyword is doing is telling the compiler essentially that it always, anytime the variable s is accessed, that it needs to actually go to memory and retrieve it. Now that might seem obvious, but it turns out it's not. In certain situations, a compiler may try to optimize our code and may make assumptions. So if it already has the value of s stored in a temporary memory location known as a register, registers are very fast and a great place to store things we're going to use often. If it already had the value s stored there, it might just pull that value and perform computation on it. By saying volatile, what we've indicated is that the actual memory location associated with the variable s could be being changed in ways that the compiler is not it cannot easily detect, and so it needs to actually go out and check that memory location. It can't just use whatever value it had on hand in the register. If that didn't make sense, don't panic. It'll make more sense as we move through the term. But just in a nutshell for now, just understand that we're using the keyword volatile to make sure that the compiler doesn't optimize our code, this particular piece of code, in a way that would hide, temporarily at least, the memory bug that we're going to see here. Okay? All right, so with the next line of code, I'm going to switch back to red here. We see then that we're simply setting the value of d to 3.14. So s.d, so this this variable d then within the struct, within our struct underscore ts is being set to 3.14, and then in the next line we are setting the ith element of the array A within S to this large integer looking value. Okay, now this number is, as has been noted here, it's possibly going to be out of bounds because we're doing nothing to make sure that I is 0 or 1. Now recall that we start counting with an index of 0. Our array A has two elements, so the valid locations would be 0 and 1. And we're doing nothing to make sure that I is 0 or 1. And so we could be storing this large number somewhere outside of the bounds of that array. And then finally, we simply return s.d. Now, if we were to run this system and print the value that we got back, here's what might happen. So here we've called fun with the value 0. So again, there's this large value here that's going to be stored at the index 0 in the array A. And this is fine, right? This is within bounds of the array. And so when we return s.d, we see that s.d is, as we expected, the value 3.14. So no surprises. Okay, if we execute it again with 1, again, that's within the range that is acceptable, and so there are no surprises. Now look what happens here, though. So in this case, we've gone out of bounds. So we've used index 2, so that's the actually the third element in an array, but we don't have 3. So we've gone past the end of the array, and something bad happened. Okay, so notice that the value 3.14 has been corrupted. This indicates to us that we've changed the data somehow. And you'll notice that if we go farther, now we're at fun 3, we've really changed it. Okay, so we're smashing bits here that we didn't mean to. All right. Now, we're still kind of close when we called fun with 2, and though we've more significantly changed the value, I would point out that even with fun 3, 2 is not horrendously different than 3.14, depending on the context, right? Now, if we're doing multiplication, this error is much more significant. If we're just doing subtraction, maybe it's not as dramatic. We don't know. The point is that this is wrong. This is not what we expected. And worse than there being this problem, you notice that if we keep going, now we're at index 4, the problem appears to have gone away. Okay, so this is like when the check engine light comes on your car, and then it turns back off again, right? It's so frustrating. Or when there's a weird noise, but then it doesn't happen again for months. So you don't know what's gone on and why you had the wrong answer, but it went away. And it's tempting to say, okay, well, maybe it won't happen again. But this is a computer. This isn't a magical box. This isn't a personality. This is a machine. And it's going to do the same thing under the same circumstances every time. So this bug is there, and we want to know what's going on. Now, you'll notice that in all of these examples, we got, in the examples of where we used 2 and 3, we got wrong answers, but the program continued to execute. In the case where the index that we gave was 4, we got the right answer, and the program continued to execute. Okay, so just because something is wrong doesn't mean we're going to know it, and doesn't mean our program's going to stop. One of the best things that can possibly happen to us if we have such a memory bug is a seg fault. Now, we all hate seeing that, okay, but if you have a memory reference bug, one of the best things that can happen to you is to have the machine crash, because now you know it and you can go in and look for it. Okay, so the results in this kind of situation are going to be system specific, depending on the operating system that's running, the applications you have running at any given time, could affect the way that this problem manifests itself. But it is a problem. You should be kind of familiar with what's going on with that kind of a memory reference error from previous courses. But as a quick reminder, I wanted to just show you a diagram of what was happening there. Now, here in the center of the screen, we've got a representation. See here, we've got a representation of memory. Okay, it's just a simple model. And I want to point out that the numbers that we have here on the right are not actually memory locations. Okay, these are going to be index values relative to, a different color here, the array here in our struct. Okay, so the first time I looked at that, I got a little confused, and I want to make sure that we don't as we discuss this. So these numbers on the right are actually index numbers relative to this array that we see stored in memory here. So index 0 is simply the beginning of the array, index 1 is the second position, and then these other numbers are the positions we would be in memory if those were valid indices. Okay? So when we created one of these, an object of this data type struct underscore t, we were allocated this memory here. Let me draw a different color there. The OS gave us this chunk of memory to store it. And we see here that the array was created first in memory, followed by the 2 words that we needed to store that double D. And you'll also notice that we've indicated here the bytes and the order that they're stored in memory there as well. So D0 being the first byte, D7 being the last. Okay, so what happened? Well, when we switch colors here again, when we first called the function fun with the index 0 and tried to store that very large value, we saw that, and I said it looks like an integer value, but it's being stored in a floating point representation. we saw that everything worked fine, and that's not too surprising to us. We were storing the number beginning at, in this location here at A0, completely legal. So we wrote stuff here. Life is good. In the second example, when we used index 1, we stored the number here, and again, life is good. Problem started right here. Because what's happened? Well, now we're trying to store this number at memory location 2. Or array location 2, which is the third element, which is right here. Okay, so there's our memory reference bug right there, is that we've gone out of bounds of the array and now we're stomping on our data. Same thing happened when we used the value 3. We ended up trying to store things here. So in both cases, we have corrupted the value of a piece of data that we didn't mean to change. You can imagine that causing all kinds of problems in any number of ways, in any number of programs. Now, when we got to the value 4, the program appeared to go away. Well, it didn't go away. We're actually at 0, 1, 2, 3, 4. We're actually now writing that data here. That didn't corrupt this data, which is the value we ended up looking at, so we didn't know that anything bad had happened. I don't know what this is. I don't know what data is stored here, but I know it's not the data that I meant to change. Okay, so in my opinion, this is one of the worst possible things that could happen, because we've now modified data unintentionally, and we do not know that it happened. This could be important later on while the program's executing. Could be 5 minutes, could be 5 days, okay, could be 5 months before the software actually tries to use the data at that location, and then we know something is wrong. But it happened 5 months ago. Good luck finding that. Okay, so as the program continued and we finally called fun with the value of 6, at that point we've marched so far away from where this was supposed to be referencing memory that we've hit some kind of critical memory location, and the operating system has now said, you're out of bounds, slaps our hand and kills our process. Okay, so again, exactly when that's going to happen is going to be system specific, and exactly where it's going to happen is going to be not only system specific, but may depend on the programs you have running. But this is just a quick refresher in terms of memory access errors and why we care. Okay. All right, so you'll note this example was taking advantage of the fact that C and C++ don't provide any memory protection. So you can end up with out-of-bounds array references, which is what we were doing there. There are other types of memory errors that you can encounter. You might have invalid pointer values, abuses of malloc and free, which can cause things like memory leaks. Okay, so chances are most of you have created or experienced these problems. We want to help you to be able to avoid them. Such things can lead to terrible bugs. How they manifest themselves is going to vary, and that makes them even more dangerous. And when they manifest themselves can vary from system to system, as well as from a particular use case to use case. How do you deal with that? Okay, well, one option is you could program in a language that keeps you from making such mistakes, right? You could, for instance, try to work in Java, which is going to prevent you from going out of bounds, and this kind of thing. That's not always an option. Okay, when you become a professional, you're going to go into a situation, you're going to be put on a project, that project's being written in C or C++. You don't get to say, hey, I don't like using those languages. It's too easy to create memory bugs. This is not the real world. You don't get to say that. And there are reasons for using these languages too. It's not just that someone's being old-fashioned. And so that's not always going to be available to you. If it is, maybe it's a good option. Don't use that language. But that often will not be a valid choice for you. So what else can you do? Well, you can try to understand what kinds of interactions might occur. Okay, you can understand the memory hierarchy. You can know the things we're trying to teach you in this class. This will arm you in a way that can help you to avoid those problems. And you can also use development tools that are designed to find and flag memory errors. Okay, Valgrind is an example of this. There are many types of debuggers and debugging tools that you can use to actually, at runtime, profile your code and figure out what's going on. Okay, so that's another useful approach. Reality 4, there's more to performance than asymptotic complexity. Okay, so again, asymptotic complexity, we're talking about just looking at an algorithm and discussing how many operations, for instance, that it has to perform on a data set of a given size, and how quickly does that grow, right? So for instance, bubble sort, if the size of the list is n, we know that the bubble sort, the amount of work it has to do, will grow in complexity at a rate of approximately n squared. Okay. It turns out that in the real world, constant factors matter. So when we talk about big O complexity, we get rid of the constants. We say, well, when this gets big, the constant doesn't matter anymore. And so this algorithm is better in all cases because we ignore that constant. Well, in the real world, that's just not how you do things, because the constant does matter. And so while in theory it's useful to talk about algorithms in that way, in practice we do need to know, well, what is the actual situation we're operating in? Bubble sort might not work real well on a list of 1 billion items, but it works great if I only have 5. There's no point in setting up a merge sort for 5 items. Okay, so we want to pay attention to these constants. The idea that I can make something work twice as fast as something else is very significant, even though that factor of 2 might disappear when we're looking at asymptotic complexity. My algorithm is 2n squared and yours is n squared. Well, yours is twice as fast as mine. I want to use yours. Okay. Also, it's important to realize that the exact op count does not actually predict performance. So 2 algorithms might actually have the exact same asymptotic complexity and perform wildly differently. And we're going to look at an example of that in just a moment. On that point, you can actually easily see a 10-to-1 performance range depending on how an algorithm is implemented. So we need to optimize at multiple levels. We need to understand our data representations, the algorithms we're using, procedures, loops, etc. In order to do optimization, you have to understand the system. Okay, you've got to know how the programs are being, how your programs are being compiled and executed. You've got to know how to measure performance and identify where the bottlenecks are. And you need to be able to make decisions to optimize performance without doing silly things like destroying code modularity and generality. What do we mean by that? Well, say you identify the fact that, hey, we're making procedure calls, and procedure calls, it turns out, are expensive. So we want our code to go faster, so we'll just get rid of all the procedure calls. All right? Well, now you have a really unmaintainable piece of code. It might be fast or faster, but you can't maintain it. Okay, so it's not useful. Or at least it's less useful. So we want to know how we can optimize performance without destroying modularity and other useful attributes of maintainability and so forth. Okay, so let's look at an example of system performance. Here we've got a simple function that's going to copy data from one 2-dimensional array known as the source to another two-dimensional array, the destination. And you'll see we've just got a nested loop here. Okay, so 2 for loops, one nested inside of the other, where we're doing a simple copy from one array location, from the same array location in the source to the destination. Okay, nothing there should be surprising to any of you. Here we have essentially the same algorithm, but you'll notice that we've switched the order of the nesting. So in the first case, the index j was being iterated through on the inner loop and I on the outer loop. In the second case, the index j is in the outer loop and I is on the inner loop. Okay, so over here we are quickly rotating, if you will, through values of j, whereas over here we are first rotating through values of I and then through values of j. Okay. you'll notice the exact same number of operations are being formed. These two algorithms have the exact same complexity, not just asymptotically. They have the exact same number of operations. Okay, you should be able to see that. Check this out. If we were to run these two functions on a 2 gigahertz Intel Core i7 Haswell, you'll notice that there is a big difference between the runtimes. Okay, a factor of 20 approximately. What on earth is going on there, right? So it turns out that computers have a hierarchical memory organization. We have registers, we have cache, we have RAM, right, dynamic RAM, and we have a hard drive, and of some kind, right? They don't all operate at the same speed, and so we want to operate in the faster memory as much as possible. And it turns out that the access patterns, the way we reference our data, will determine to a large extent how often we're getting data from the cache versus from RAM, from our dynamic RAM versus from the hard drive. Okay, and so the way we step through, for instance, a multi-dimensional array, whether we're doing it by row or by column, can greatly affect speed. And so this should convince you of that. I mean, that's profound, the differences there. All right, and where was that caused? What decision resulted in that? It wasn't the compiler, it was the programmer, whether they chose option A or option B. Both get the work done, one gets it done fast. Okay? Finally, our last reality is that computers do more than execute programs, right? We don't set them off in a corner and plug them in and let them just go. No, we interact with them. We give them information and we get information out. Okay, so I/O systems are critical to the reliability and performance of a computer. Computers communicate with each other over networks. This is increasingly true. We're living in a world where computers are part of so many things we interact with. You know, no one would have thought of a few decades ago. No one would have thought of their phone as a computer, but now it is in every sense of the word. And these computers are connected over networks. Many of the problems that we have actually come from the network and the way we interact with the network, as opposed to the CPU itself. So we need to understand these things. We need to understand the kinds of things that happen when we have concurrent operations. Okay, things happening at the same time by different processes, possibly on different machines, communicating over a network. We need to know what can happen when information is not communicated or stored properly. What will happen to our programs, and how often is that going to happen? How can we deal with it? We need to understand how systems that are different, running different operating systems or storing numbers in different ways, how can they communicate with each other? And if they do so improperly, what will the ramifications be? And then also we have performance issues, complex performance issues. We have decisions to make. For instance, maybe we have the option of splitting up a problem across multiple processors connected by a network. But it takes time to send data back and forth over that network. And so there's a balance to be found. If we do too much work on a single processor, then we create a bottleneck and we're not taking advantage of the other CPUs that are available. But if we farm out the work to do ineffectively, then we might be spending so much time sharing results between the processors that we don't get any speed up. Okay, so there are some complex performance issues that have to be understood and ironed out. Okay, so these are just a taste of the kinds of decisions and the kinds of problems that we can encounter when we're working with computers. This class is designed to help us understand computers in such a way that we can take advantage of our understanding to improve performance and also be able to avoid potential pitfalls that come from not understanding the computer. Okay, I thank you for watching. These last two presentations were intended to motivate the rest of the course. In future presentations, we're going to get into these topics at a meatier level and begin actually doing homeworks and labs based on them. I hope you are looking forward to this class. I promise you it will be very rewarding, and I look forward to working with you. So until I see you again, thanks, and have a good day.